So we return now to optimization techniques, and now we're going to focus on what are called derivative-based methods. Okay? So, and in particular, we're actually going to consider this what are called unconstrained optimization problems. Okay? And these are derivative-based methods. Okay. So in the last lecture, what we talked about are optimization techniques. We did golden search. We did not only golden search, we did success of a parabolic approximation, where we really never made use of the derivative itself. Now, what we know about a function, right, is that if you want to find a minimum, just look for where the derivative is 0. Which is great as long as you know explicitly what the function is. In the derivative-free methods, you don't even have to know what the function is, and you can still apply those techniques. But now, suppose we do know what this is. Then we can start applying this directly here and thinking about a technique whereby we can actually do some kind of iteration technique towards get to the solution based upon the derivative. Now remember, what we're trying to find is the minimum of some vector-valued function f of x. So what we really need is a generalization of the derivative of 1D to higher dimensions, which isn't that hard to find. If you do multi-dimensional calculus, multivariable calculus, what you're going to find is that the generalization of the setting the derivative to 0 is to compute the gradient of this function equals to 0. Okay? And what the gradient is the partial derivative. I can define it for you. This thing is going to be something like df dx in the x direction plus df dy in the y direction plus df dz in the z direction plus how many ever directions you have, that is the definition of the gradient. What you produce by doing this gradient computation is a vector. Let's keep that in mind. The gradient produces a vector. Okay? And what you're looking for that vector to be is 0. Okay. So I'm going to give you an example. And often, this methodology we're looking at here can also be called gradient descent. And by the way, gradient descent, or generalized method of residuals, GMRes, if you recall back to the iterative techniques for solving ax equal to b, this gradient descent method is very closely associated with the iterative technique of generalized method of residuals and also biconjugate gradient stabilized method by CG stab. So these high-end sort of iterative techniques is what they're doing is actually doing what's called this gradient descent, trying to find the solution. And let me try to draw kind of what this looks like. So today is going to really challenge my drawing skills. And so let me try to see if I can pull this out. Consider the following function that we might want to try to minimize as an example. And I'm just making it easy so I can actually draw it easily too. X squared plus 3y squared. Here's a function. And by the way, the minimum is at the origin. Okay, so I know this ahead of time. I've constructed something that's easy. Okay? So what does this function look like? Let me try to draw this in 3D. Suppose the origin is here. Okay, so this is the value of the function f. And let's say this is x and y. Well, this is a parabola in both directions. So if you want to think about it, it's sort of a kind of looking like a taco. Oh, something like that. You know, that's about as good as I'm going to draw it for you right now. Okay, actually no, I'm going to draw it for you better because I have to fix this up. Let me draw this a little bit more like this, a little more like that, and then like this, and let's just say this is the origin down here. Wherever this thing looks like it's sort of at the bottom, I don't know, right there. Let's just say that's the origin right there. Okay, so it's this, this should come up a little like that. Okay, so it's like this parabolic surface this way and this way. In one direction it's x squared, the other direction is 3y squared, so it's a little faster in the y direction than the x direction. And there you go. And what you're trying to do is find this point. Now if you do a top view and you look at what are called isosurfaces or surfaces of constant amplitude, then what you're going to get if you look from the top view, again here's the origin at 0, 0, you're going to get basically ellipses. Okay? So x, y. So that's that top view. So you're looking at surfaces of constant amplitude. And what you want to do in this gradient descent is find an algorithm which basically amounts to sort of rolling a marble downhill so it gets to the bottom of this parabolic structure. So the way you can compute sort of the steepness at any point in this place is, if you want to compute what's going on there, you compute the gradient. And if you compute the gradient on the surface, what you find is the gradient looks like this. It's radial, and the further away you go, the gradient's bigger the further away you are, smaller when you're inside. Hopefully this conveys the picture. So the gradient, how rapidly it's changing, gets bigger away and it's pushing away from this structure. Okay? So that is kind of what we want to start thinking about in this thing here. And by the way, these gradient lines don't necessarily go through the origin. In fact, this gradient line here can go through and can cut across like this. I kind of drew these coming out of the origin, but those are very close. But you have gradient lines that cut across like this. So let me draw that in red. Might have a gradient line coming screaming across like that. So what does this correspond to? Well, suppose I draw a gradient line here. It might be something where it's coming down and coming back up again. So what I want to do in this gradient descent is this gradient tells me the fastest direction of either growth or decay. So what I really want to do is I'm going to start with a guess for a solution. And from the guess of the solution, what I want to do, here's the philosophical point of view for this method, is that I want to start from some guess. Let's start here. Here is my gradient. I want to move against the gradient in this direction. So the gradient's going that way. I move against the gradient down this way. But by the way, when I go downhill, and then I start going back uphill again. So what you'd really like to do is go downhill till you get to the minimum. This thing is a parabola, and you want to find, oh, here's the bottom. And once I get down here, now you're going to go to the next gradient line. Maybe that's that direction. So you go from here, you go downhill to here, and then you go downhill to here, and then you keep going downhill. You want to always keep going downhill. So the question is, how do you find this direction? When do you know to stop? And then switch to another gradient. So that you're always going downhill. Because if you go down this gradient line, you'll go past here and keep going up. You'll start going back uphill again. So you get to the bottom of this hill, keep going to the bottom of that hill, bottom of that hill, bottom of that hill, and then get down to converge here. That is the gradient descent algorithm. Let's illustrate that. Hopefully I didn't butcher that too much, but in the notes you'll actually see some nicer graphics showing you how this thing looks like, showing you how you ride these gradients. And so you'd want to go downhill to here, but maybe the gradient from here goes like this. You go downhill to here, then you ride this gradient here, downhill to here, and downhill. And you try to get to that point. Always going downhill. So how do we always go downhill? Well, let's start calculating this out. So what we want to do is start thinking about this gradient. So let's go ahead and take this specific example, right? So we have this example of f of xy is equal to x squared plus 3y squared. And so the gradient is basically df dx in the x direction plus df dy in the y direction. Well, what's that? df dx is 2x x hat plus df dy 6y y hat. Okay? And x hat and y hat are unit vectors in the x direction, unit vector in the y direction. Okay? Now, how do we want to think about this? The direction I want to move is opposite to the gradient. If you remember, the gradient's going away from the minimum. So I want to start thinking about an algorithm where I say, where do I pick my next point? Here's going to be my next point, C, which depends on some parameter tau. And I'll tell you what tau is in a minute, which is my current location minus tau times the gradient of f. This is a very important formula. What's it telling us? What should my next future point be? Well, I start where I'm starting, minus, I go the minus gradient, so it's going in the direction opposite the gradient, and I go a tau amount of it. I don't know what tau is yet. We're going to have to figure out how to calculate tau. But come back to the picture. That's the picture. You're going downhill. This is the minus gradient, so I start here at x. This direction is the minus gradient, and what I want to do is go all the way down here to here. I want to go tau amount of this gradient, so that end up there, and then I switch over, and now I have a new tau, and then a new tau, and I try to get down to here. So I don't want to just keep going this direction. I want to go this direction just the right amount. Okay? So this here sort of is the basis for the iteration. Or, if you prefer, it's the basis for iteration. It is the basis for making yourself go downhill at all times in this gradient descent. It's always looking to go downhill. And the only thing you've got to figure out is how would I compute that parameter tau? Well, what we can do is imagine another function, f of tau, which is this function f, which is a function of this new point, right? So I imagine a function tau, which is my function f evaluated at this new point. Well, this new point is a function of tau. So then I could say, how about I compute the following? What am I going to do again? I'm looking for the bottom. I'm looking for where this thing is at the bottom. In other words, where it's minimum. Whenever you say, I'm looking for something that's minimum, you should start thinking instantly that there's a derivative going to be 0 there. Okay. So that's what we have. I'm looking for this something to be 0, and what I'm looking for, I'm taking df dt of this thing, and if you do your chain rule, that's going to be gradient of f xc times gradient f of x. You want this to be 0. Use chain rule, this times the derivative of that. That's how you get this thing out here, right? So, okay. Here's what's kind of interesting. This is a vector. This is a vector. I take these two vectors, and I'm multiplying these two vectors, which is here. It's like an inner product. And the inner product is 0. What does that tell you? if the inner product between two vectors are 0, it tells you they are orthogonal to each other. Does that make sense? Well, let's go take a look. I'm trying to go down this hill, and then I'm going to take off. So I didn't draw it that well, but this direction is going to be orthogonal to this direction. So right here, I want this thing to actually go this way, then go this way. It's going to be an orthogonal direction. That's what this thing tells us. I didn't draw it well here, but you'll have to forgive that. That tells me about orthogonality of those two. Okay? So let's go ahead and compute this for this specific example here, because for this specific example, I can compute the gradient, I can compute this new point, and then I can compute such quantities as this. So let's go ahead and do it. C is equal to x minus tau gradient f of x. We can evaluate this because we can actually compute this. In fact, it's right there. X itself is, two components, x1, x2. I take the gradient of this thing here. So this vector x, right, is two components, x, y. And then this thing here is this gradient is this vector right there. And then I have a tau. So by the time you get done with this calculation, which is not very hard to do, what you have is 1 minus, oops, sorry. 1 minus 2 tau x in the x hat direction plus 1 minus 6 tau y in the y direction. So the 1y and the 1x here comes from here. And then I have the minus 2 tau from the gradient and the minus 6 tau from this gradient with the tau. Okay? Now from this C, I can then plug it into here and evaluate f at that value of C. That's going to give me my f of tau. Okay? So take this C, and then you're going to basically take this thing and evaluate f at that point. Okay? So your f of tau is equal to f at C tau. And by the way, when I think about evaluating f, look here at f. F is this thing here. It's x squared plus 3y squared. X is the first component. Y is the second component. Well, in this case, what is my x? Here's my x component. Here's my y component. Those are going to be the pieces that go into the x squared plus 3y squared. So what I'm going to get is 1 minus 2 tau squared x squared plus 3 times 1 minus 6 tau y squared, there. So you get this formula here. And so all you would really want to do now is calculate the derivative of this thing, f prime of tau, which is minus 4, 1 minus 2 tau, x squared, minus 36, 1 minus 6 tau, y squared. And you want to set this to 0. Hey, once you do that, you're going to get a value of tau. And tau is going to be the following. You solve for tau here, and tau is going to be x squared plus 9y squared all over 2x squared plus 54y squared. Done. Because once we have this tau, notice what happens. I can just say take that value of tau, use it right there. And here's my iteration scheme. So I want to write a program to do this. How do you do it? Here's my current point. Here's my next point. I start from here, and to get my next point, I take this minus the tau I just computed times the gradient gets me my next point. Now my next point becomes x, which gives me, you could just follow this along. That's it. It's whole gradient descent. Nothing else that fancy about this thing. Okay? The one thing I'm going to point out, again, is that this kind of methodology is the kind of thing this essentially trying to reach the bottom of this well is exactly what's at stake when you try to solve ax equal to b using gradient descent methods. In fact, what you really do is you write this in a quadratic form, an equivalent form of this in a quadratic form. And when you do that, when the quadratic form, what you end up getting is some kind of surface like this in principle in the quadratic form. And you just try to find your solution by falling downhill. How do I find a way to get down to the bottom of this hill as fast as possible? So this method here is just gradient descent. You go down the hill, switch. You always go downhill. Some of the methods, like GMRes, BiCG-STAB, have a little bit fancier ways. You say, well, I'm going to go down this hill and this way. Is there any way I could kind of shortcut this? You know, kind of like, instead of going down this hill and then down this hill, could I have, you know, kind of point more towards where 0, 0 is the entire time? Okay? So I'm not always just going as fast as I can downhill, but I'm moving more, in fact, towards the target area, which is the origin. Okay, so that is the gradient descent algorithm. And in fact, let's go ahead and program this thing up, because it's a good exercise to do. All right. So we come over to the computer, and we're going to execute this and see how well we do. All right, let me pop this thing open here. And uh-oh, there, okay, got it. Okay, so let's come over here. I'm still working on the previous lecture. Let's kill all this out. Clear all, close all, CLC. Now let's go ahead and take a function. Let's go ahead and take the function that we had in mind, and let's actually try to plot this thing just to see what this thing kind of looks like. So the way you would do this is you have these x and y variables, and I want x to say, let's go from, I don't know, -3 to 3, and y will go from -3 to 3. And there's this command called mesh grid, which will make this two-dimensional. So what the mesh grid does, and you can look this up in some of the higher dimensional plotting algorithms, is x and y don't know that they're the x and y direction. When I put them in mesh grid and generate capital X, capital Y, they actually now have directionality. They know that one of them's in the x direction, one's in the y direction. And so now I can plot the surface. I can say f is equal to x squared plus 3 times y squared. And it's a 3D plot, so we can say something like surf x, y, f. And let's see what this thing looks like. There, look at that. That is what we're trying to find the minimum of. Look at this. Ready? I'm going to rotate it. Oh, you're getting dizzy? Okay. There it is. There's the surface. And what are you trying to do? You're trying to fall right into the bottom, right there. Okay? So this is what we have. And what we're going to do is we're going to keep track of this algorithm by plotting this once in a while. We're going to take a guess, where we're going to start off with some guess. We're going to try to roll the ball downhill. Okay. So let's leave that alone for a minute. And let's start off with a guess. Let's say that x1, my first value of x1 is 3. First value of y is 2. And this is just a guess. Make up anything you want. Okay, so I'm just saying, let's suppose the solution was at 3, 2. And let's see what happens. Let's iterate forward. What I have to do is evaluate what this function is at that point. So f is equal to, well, it's x1 squared, right? Plus 3 times y1 squared. By the way, I could just say x and y, but I want to keep track of my values so later on when we go plot this thing, we can actually see how well we did. Okay. So there is the function. Initial value. So we could actually put this point up on this surface. We could say surf, let's do a hold on here, and let's see where this guess is. Surf x, y, f. And let's make this a big black circle. Line width. Three. All right, let's see if that works. Oh. Okay, I see. Let's do F1 here. Let's call this, instead of F, let's do F surf. And this will be F surf. And now it won't get confused with F. Hopefully. Oh, you know what? We have to do plot 3. Okay. Or maybe not. Oh, okay. Sorry. So this is my initial guess point. See, it's interfering with this x here. So we want to let's clear the x above and clear the y above, so it shouldn't interfere now with this thing. All right. So there's my guess. See that? There's my guess. All right. Good. Got worried there for a bit. See that black ball right there? That's my guess. Let's bring it over a little bit. Let's make this guess be not 3-2, but like maybe 2-2. And if we guess that, and I think we want to also put some semicolon there. There. Okay, see that black dot? That's my guess. You can clearly see that it's not at the minimum. But I want to get this black dot to roll downhill into here by guessing correctly. So let's go ahead and build a code that does that. So now I got a loop for j equals 1 to 100, let's say, and I'm going to do it. So here's my for loop. I'm going to iterate to try to get the solution. So first I need to calculate what tau is. Tau is pretty easy to calculate. It's basically x of j squared plus 9 times y of j squared. So remember, we're going to start off with j equals 1. And by the way, if j is 1, I have x1 and y1. So that's up here. I already have defined them. Divided by, and on the bottom I have 2 times x of j squared plus 54 times y sub j squared. There, that's what my tau is. We just computed that. So my new values, if I look at my xi values, my x of j plus 1 is equal to what x of j used to be, plus, or so minus tau times the gradient term. And we actually computed what this thing looks like. If you remember up on the board, the xi is 1 minus tau x. Okay? Let me actually, x of j plus 1 is actually, if you remember, we computed it up on the board. It's 1 minus 2 times tau times x of j. And my y sub j plus 1 is equal to 1 minus 6 times tau times y sub j. And my f of j plus 1 is equal to x of j plus 1 squared plus 3 times y sub j plus 1 squared. That's it. Here's my update for x. Here's my update for y. And by the way, where did we get that? Let's come back over here to the board. If we look over here on this board over here, thanks. Remember, I computed xi is equal to x minus tau. I put in this value here to get this. Here are my new values. My new x, my new y. Remember, xi is my next point. So this is what I did. 1 minus 2 tau x, 1 minus 2 tau y. That gives me my new point, and I just can keep updating this. This is the loop. Compute a new tau, compute this. Compute a new tau, compute this. Compute a new tau, compute this. And this will iterate down towards the solution. Okay, So we have this, and then what we want to watch is to see, watch this thing converge. And by the way, how do I know if I've converged? Because you don't want to necessarily go through this 100 times. You should be able to stop this at some point. One way to check to see if it's converged is ask the following statement. If the absolute value of f of j plus 1 minus f of j, in other words, if the f values are converging to each other, then you'd think that, well, if they're converging to each other, that means you've converged to a solution. Is less than 10 to the minus 6. Break. Okay, that's it. And now we're going to do one other thing. Every time we do this, we're going to do a plot 3. Actually, we don't need to do a plot 3 here. We're keeping these as a vector, right? So we can just, well, we can. So let's do the following. Copy and paste, Control C. Right here, we're going to plot this new value. And we want to plot x of j plus 1, y of j plus 1, f of j plus 1. And let's go. Let's see how this does. And by the way, why don't we do this? Pause for 2 seconds. So we're going to pause for 2 seconds so you can see what happens during this process, and go. All right, so here's the problem. All right, so it was kind of hidden behind there. So let's get a different view angle. Let's get from that view angle right there, which is about negative 7550. View. Let's see if this will work. Okay. So there we go. See this? There's a new point. There's a new point. And see, already at the bottom. So that wasn't that much fun, because you see how it went from here to here to here to here. This is your gradient descent. This is how this thing fell into the bottom of this well. Your gradient descent worked here very nicely. We actually, like I said, I plotted it here. 1, 2, 3, 4, 5. Fairly fast algorithm to get down there. In fact, how many iterations did it take? 9 iterations to get within 10 to the minus 6 of the solution. Okay? So this gradient descent was always looking to go downhill, and it actually did a very nice job. And notice, by the way, did it do the right thing? Notice where I went from here. I went from here down to here. So it went all the way downhill. And if I kept going past this point, I'd go uphill again. So what did it do? Right here, it stopped. This is how we discovered the tau. The tau told me where that point was. Once I get to that point, I want to go downhill again. And now I'm going downhill from here down to here. Okay, and once I get down to the bottom of the hill, stop, go downhill again. Anyway, that's the gradient descent. Maybe I can actually even make this a little bit bigger so you just see it. Okay. So that is the application of that technology, or this methodology. Okay, so you have a gradient descent algorithm that you have available to you. The other one I want to talk about is, okay, so that's gradient descent. It is an algorithm that is based upon derivatives. You compute a derivative. Let me tell you the other one that basically is something like this. It's fmin search. And by the way, we've already played around with fmin search. And fmin search is very much closely related to this gradient descent. But it has some more bells and whistles. But I want to talk about how it works. Because part of what fmin search does is that it allows you to sort of solve, optimize nonlinear problems. Okay, so this is a pretty nice method, fmin search. In fact, I would say, for the most part, if you have an unconstrained optimization problem, in other words, you want to say, I have this function, and it has a bunch of variables in it, and I want to find the values of the variables that give me the best objective function, well, fmin search is usually a pretty good place to start. It relies on a guess. Anything that has a guess should already be a tip-off to you that if it has a guess in there, that if you got a guess, then it means you're going to do iteration. Okay? You're going to start from that guess and you're going to try to work down to the solution. So how does fmin search work? Well, let's talk about the basic algorithmic structure. Fmin search, what it wants is an objective function. You tell it, what are you trying to minimize? Okay, so it's going to minimize something. You get to tell it. Second, it wants an initial guess. And that's about it. Tell me what you want to minimize, give me a guess, this can be nonlinear, and I'll go find it for you. Let me give you an example. In fact, we're going to do this example here on the computer. Suppose I have data like this. What kind of function might you pick to do this? Well, it kind of looks sinusoidal. So you can imagine picking a function like a cosine. In fact, that's what we're going to do. And you could pick kind of a cosine function that might look like this. You could say my f of x that I want to pick for this to try to fit is a cosine bx plus c. So right, the c is sort of this offset. How far up am I? Because normally a cosine oscillates around 0. Well, this isn't oscillating around 0. It's oscillating around some mean value here, which would be like our c. This is our amplitude a. And what does b tell you? It tells you the period. Well, a period here is like 2 pi. That's be something like that. That kind of makes sense? So I have this data. I'm going to try to fit this to it. And I got to pick a, b, and c so I get the best fit. Now, this is a very nonlinear problem. I got to try to fit this onto here. And by the way, when I try to do this, the guesses I have for a, b, and c really matter a lot. But I can get very good guesses, right? If I look at this thing, I can start estimating what should a be, what should c be, what should b be, directly from the data. So I want to do that. I want to evaluate this. And by the way, the objective function I give you is a function. So I have to know the function I'm actually trying to minimize. Okay? So we're going to do a curve fit again. And we're going to try to actually fit that curve onto there. So that's going to be our objective function. We're going to minimize the error. So let's go ahead and solve this problem just so you can see how this works. And by the way, again, this is an example. And I like to do fmin search because it's such a powerful routine that it's something you should just simply know how to use and be exceptionally well versed in. All right, so let's take some data. I want to take the following data. X equals 1 to 24. It's going to be like, say, temperature data. Over a 24-hour period, the temperature goes from 75 to 77 to 76, 73, 69, 68, 63, 59, 57, 55, 54, 52, 50. 50, 49, 49, 49, 50, 50, 54, 56, 59, 63, 67, 72. Let's make that up. This is just like plot x, y. And so there's my data. Let's just say that that was the temperature fluctuation through the day. Here is sort of the peak of the day, night, back to day. Now clearly what I have here is just data that looks very much like that fit I just actually advocated up there, which is sort of an a cosine bx plus c. Sort of a simple cosine fit, but you can't do this with your standard minimize some function. This is going to give you a nonlinear set of equations if you try to do something like we did with the least square fit technology. We need something a little higher end, and we're going to use this fmin search, which is essentially doing gradient descent. You're going to give it a guess, it's going to figure out which way to go, and it's going to go that way to try to give you the best solution. All right, so there's my x and y, and what do we want to do? Well, we want to go ahead and calculate the values of A, B, C? Well, so first of all, let's look at this thing. What are good guesses for A, B, and C? C is kind of the offset from 0. Well, like if you look at an average value here, it's probably around 60, 62, somewhere in there. So let's go ahead and pick that. Let's just say, how about we pick 60 or 62? So let's go ahead and suppose that, actually let's do the following. We'll put a hold on to this. We're going to plot this. Let's say C is 62. What about A? Well, A is the amplitude around the average. I'm going from about 62 up to 77, all the way down to 50. So I don't know, 12, 13, 14, something like that. Let's just pick A is about 13. That's the amplitude. So right, I get these amplitude fluctuations around the mean. The mean's around here, around 62, and I have about 13, 12, 13 on either side. And B is more interesting because look at this. This is almost a whole period. In 24 hours, I have 2 pi. So said another way, I have B times X. Well, this is like 2 pi, right? I want this to be something like 2 pi. And X is going to be 24. Does that make sense? So in a period, in other words, in my data, I go from 1 to 24. So that's the X, cosine BX. The X is 24. And that corresponds to something like 2 pi. So if I solve for B there, B would be something like 2 times pi divided by 24. Or pi over 12, if I want. There you go. These are just estimates. Let's see how well our estimates do. Because now I could say, how about I make my function f is equal to a times cosine b times x plus c. And I can plot that, x, y, and let's make this in magenta. There you go. Oop. Sorry. Plotting f, not x, y. Okay, go. There. Okay, so there was my guess, and there's the actual solution. So, you know, it wasn't like, you know, I didn't do so bad, but I certainly didn't do well either, right? If you look at that thing, it's okay, but it's clearly not the minimum solution. But the minimum solution is going to be kind of tricky to get unless I use some kind of optimization routine. I don't want to just be guessing A, B, and C. I want to actually go figure it out what, in fact, is the optimal solution. So let's go do that. So what I want to do is take those values of A, B, C and use those as my guess. So fmin search is going to call some right-hand side function. Let's call it data fit. And what I want to do is give it the guesses, A, B, C. Oops, sorry, I can enter it as vector. I'm going to give it the guesses A, B, C that I have. I'm not going to send any options in, so I put that. And that's what we talked about last time. And then I send in x and y, so the data is going to go in. And what is going to come out is my coefficients. So my coefficients are going to come out. My first component of this is A. The second component of this is B. And my third component is C. And then I could just do this again. Plot. Here, let me copy and paste this. Once I have those, I can say, let's plot F2, which is A1 cosine B1 plus C1. OK. Good? So that is what I've got to plot after I come out. So I'm going to plot then X versus F2. And we'll plot that in green. OK, the only thing we have left to do is build this data function. So let's go File, New, mFile, Function. And what I'm trying to compute is minimize some error, data function. What was it I call it again? Sorry. Data fit. Data fit. And what I'm sending in here, right, is my initial guess is x naught plus x and y, which are my actual data. And A is equal to the first component of x naught, B is equal to the second component of x naught, C is equal to third component x naught. These are my guesses. Remember, I sent in a vector with 3 components of guesses A, B, C. So that is here being sucked up by x naught, which is these 3 guys right here. I rewrite it. What am I trying to minimize? Well, what I'm trying to minimize is the least square fit error, which is the difference between my solution and my solution. What does it look like? My solution is this A cosine bx plus c, right? So I can say A times cosine bx plus c. That is my solution, minus the actual values, squared. So I square that, and then I got to sum it. Sum it. And that is what we have. That is that's what we're trying to minimize. Okay? So you take the vector, you square it, you sum it, and if I can make this minimal, then it's going to give me back an ABC that I want. So let's file save that. Save as datafit.m. Save. Okay. So let's come back out here, and let's go ahead and run this. Okay, look at that. It worked on the first try, which is actually kind of like miraculous. I think you guys should be totally impressed the number of times I'm actually getting on the right time. Of course, I'm kind of following the notes, so you might say I'm cheating. On the other hand, still, I should get some credit. Look at that. Notice what you have. You have the data points here in black dots. You have this guess that I had was this magenta curve. And you see the blue curve? That is your least square fit using the fmin search command. Let's talk about the fmin search just a little bit. The fmin search is actually kind of it's a nice command. It's based upon this what's called the Nelder-Mead simplex method. And it's a way of doing nonlinear curve fitting. So it's a very powerful technique, and it's available to you there. I mean, if you're going to do optimization, one of your first things you want to ask about if you're going to do optimization is just do an fmin search. Can you actually fit things into an fmin search? Notice fmin search doesn't allow constraints. So this is a class of optimization problem where it's unconstrained, right? I'm looking at all parameter values. I'm trying to get down to a solution. One of the problems with optimization is sometimes you have constraints on the system. You say, look, I'd like to find a solution in the best one, but I have constraints that I have to satisfy. This isn't having to satisfy any constraints, and so it's actually a lot easier to do. Okay, so we're going to get into some higher end techniques in the next section, but you can see what this does. This is really producing the gradient descent, or the fmin search, is all about an iteration structure where you give it a guess, and you start rolling downhill. That's your whole point. Start going downhill. Try to reach the bottom of the function. And in this case here, what we're rolling downhill towards is trying to get the bottom of the error function. Okay? When we do this curve fit, fmin search rolls downhill, finds this minimum, gives you back things. And it does it pretty efficiently. You can see how fast that was. And so you want to use these kind of techniques as often as you can. And I think that's about it for the derivative methods. In the last lecture, I'm going to introduce you to some MATLAB functionality for problems that are constrained, and also problems that are highly that are very complex in trying to do any kind of standard optimization procedure.